So this is the beginning of our discussion about section 9.2, Sum and Difference Identities. We're going to start using the Greek letters alpha and beta to represent two angles. And I want to get started here by asking the question, is sine of alpha plus beta, so is sine of the sum of two angles, related to sine of alpha and sine of beta, the sines of the two angles taken separately? And I think if you pose that question to me, I'd say, well, let's try to make a guess here. Is it always true that sine of alpha plus beta is equal to sine of alpha plus sine of beta? Can we just add those signs separately and get the same thing as the sine of the sum of the two angles? It seems reasonable to me. This is sort of like those exercises where you were asked to prove or disprove an identity. Prove it if it's always true. To disprove it, you have to find values of alpha and beta that would make the equation false. It's not too hard to disprove this one. In fact, what if I set alpha equal to pi over 2 and beta equal to pi over 2 and plug into this equation on both sides? What I would be writing then is sine of pi over 2 plus pi over 2. Is that equal to sine of pi over 2 plus sine of pi over 2 separately? Well, pi over 2 plus pi over 2 is just pi. So on the left-hand side, we're calculating sine of pi. We know sine of pi is 0. On the right-hand side, we're evaluating sine of pi over 2 plus sine of pi over 2. And sine of pi over 2 is 1. So 1 plus 1 is 2. 2 is not equal to 0. So as far as our guess or our question, the answer is no. It is not true that sine of alpha plus beta is equal to sine of alpha plus sine of beta. And it's unfortunate, but that's a fact. And so we need to investigate this a little further. Turns out there is a relationship, important relationship between sine of alpha plus beta, sine of alpha and sine of beta, but it's more complicated. And it's something we're going to be talking about quite a bit. I'm just going to give it to you here so we can take a look at it. It's called the sine of the sum of two angles identity. And it reads like this: sine of alpha plus beta is equal to sine alpha cosine beta plus cosine alpha sine beta. So it's quite a mouthful of terms there. Notice there are two terms being added on the right, and I just want to point out we have a sine alpha and we have a sine beta, kind of like in our guess, sine alpha plus sine beta, but in the actual identity, the sine alpha term has another factor, cosine beta, and the sine beta term has another factor, cosine alpha. So it's actually this combination of four separate sines and cosines that gets put together to be a quantity that's equal to sine of alpha plus beta. Now what I'd like to do is take a little bit of time to derive this identity, and this is optional material. So if you want to just skip the rest of this video, move on to the next, that's perfectly okay, because you're not responsible for the derivation of this identity. And so let's go ahead and, for those of you who are interested, let's continue. We're going to go ahead and derive, and I'm putting on the screen now a handout that's posted in Canvas, and it's my version of the derivation of this identity. And one thing about it is the notation here is a little bit different. So this handout refers to sine of x plus y. So instead of alpha and beta, this handout is using x and y. You could change all the x's to alphas, all the y's to betas, if that would be easier for you or make more sense to you. And just realize there's no functional relationship here between x and y where y is a function of x. Here, x and y on this handout are both like values of the input variable. They would be both like quantities on the horizontal axis. So maybe it's unfortunate we're using y here, but actually it's also not such a bad thing that you get used to seeing y being used in this way. So y is not a function of x, y is not the output of sine here. X and y just represent two angles, just like alpha and beta. So let's go ahead and get started on this derivation. Now, this derivation that I'm going to show you that depends on the diagram here is only works for acute angles where x, y, and x plus y are all acute angles. The identity itself works for all possible values of the x and y, positive, negative. They don't have to be angles that could appear in a triangle at all. And so this is not really a complete derivation. It's only a partial derivation, but it also uses some interesting geometry, and I think it's a good kind of way to get a bit of a handle on what's going on with this sign of the sum of two angles identity. So I want to talk a little bit about where this picture comes from that we're drawing. So we have angles x, y, and x plus y, and we want to draw them in a picture. So I'm going to use a horizontal line to be the initial side of the angle x. Then I'm going to draw the other side of x like so. So there's my angle x. Now, right next to x, I want to add the angle y. So this second line I drew is going to be the initial side of y, and then the terminal side of y is kind of go up like that. So there's my angle y. And because I drew them in this way, if I go from the initial side of x to the terminal side of y, that's a copy of x plus y in this picture. Now I'm going to add some more lines to the picture. One thing I'm going to do is I'm going to draw perpendicular straight down to the horizontal from this one spot. It could be anywhere along this terminal side of y. There's no length measured out here. I'm just picking a point and coming straight down. And then I'm going to add a couple other bits of information to my picture. Let me just extend these lines a bit here. What I want to do from that same point, I want to draw another perpendicular line, but this time to that side that lies between the angles x and y. So I'm going to come down at a right angle to that side, like so. And now I'm going to add a couple more lines to my picture. From this point we hit here, I'm going to draw another perpendicular straight down to the horizontal, the base of our picture. And I'm also going to draw a line straight across, so that will form right angles right there with this one vertical line. So I have like a horizontal line and a vertical line there. So I have a whole bunch of triangles in this diagram right now. And what we actually have a whole bunch of copies of the angle x all over the place. So I just want you to think about notice how this angle here and this angle here are equal. So if I look at this triangle that has an x in it, and if I look at this triangle, so they're both right triangles. Here's a right angle, here's a right angle. They both share this angle, this corner and this corner. If two angles of two triangles are equal, then the third angles have to be equal. The third angle below is x. The third angle on this triangle up above must also be x. So that must be a copy of the angle x. And now I think what I want to do is describe some trig function values for some angles in this picture. And there's actually more than one way we can describe these trig functions. For instance, sine of x using just SOHCAHTOA, where we think of sine x as being opposite over hypotenuse in a right triangle. You know, there's more than one right triangle containing x. Oh, I guess I want to label some of these points first. 0, A, F. I'm just copying my picture on the handout. D. This point right here is E, and C. I think that's all I need. So sine x, what I'm going to use in the derivation is actually this larger right triangle containing x. So the opposite side is DF, and the hypotenuse is OD. I also need to express cosine x. Now, I'm not going to use that triangle. And actually, I'm not even going to use the other triangle. I'm going to pick, here's a third triangle I'm going to shade. Notice the slight difference here, where it's actually triangle ECD, or DCE. So I'm not using that little piece below here. So this is a right triangle that contains the angle x, and so its cosine is its adjacent side, or CE, over its hypotenuse, which is CD, is cosine x. Sine y I need, and for sine y, it's actually, I only see one right triangle with angle y. So I think I have to use the opposite side as CD over the hypotenuse is OC, CD over OC. And cosine y, cosine y is, again, I got to use that same kind of going around the outside here, right triangle containing y. Adjacent side is OD over the same hypotenuse OC. And then we also need an expression for sine of x plus y. Now x plus y is an angle with this side and this side. And I think I only have one right triangle with x plus y in it right here. And sine, so I need an opposite side. That's side AC over the hypotenuse is OC. Okay. And so now I'm going to go back to the handout, and maybe even zoom in a bit. And let's see if we can work our way through this this chain of equivalences. So we just said the sine of x plus y is AC over OC. We saw that in our diagram. I can rewrite side AC as AE plus EC. That's just AE plus EC. I'm just breaking it into two pieces over OC. And then we can take that apart as the sum of two separate fractions over the denominator OC. And now I'm going to make a change. I'm going to replace AE with DF. Now why can I do that? Right here, this shape, maybe I got too many marks in here now, but AEDF is a right triangle from the way that picture is drawn. So AE and DF have to be equal to each other. It's a little easier to see in the original diagram. So I make that switch. I replace AE with DF. And then what I'm going to do is DF over OC, I'm going to multiply by OD over OD. That's equal to 1. Plus EC over OC, I multiply by CD over CD, also equal to 1. So I can do that. And then I'm going to rearrange the denominator. Since I'm multiplying these fractions, DF, OD I leave alone, but OC, OD I can interchange. It's the same product with OD here and OC here. And I rearrange the denominators of the other product. It's still the same with CD here and OC here. And now when I look at DF over OD, that's our sine x. OD over OC is cosine y. EC over CD is cosine x. CD over OC is sine Y. So there we got it. From that diagram, we got our trig identity involving the sum of the sine of two angles. And I'm gonna, I can, it just really doesn't work to put, because I have to back out so far. There we go. You see most of that. And so that's the end of this portion. We're going to continue this story in the next video.